Let's work some examples of triple integrals. So the first problem I'm going to do is problem 11. We have the triple integral of the function z over x squared plus z squared, where we're integrating over e, is this region that we have here. Now, let's actually go ahead and sketch out that region, and we'll make use of GeoGebra to do that. So I'm just going to kind of type in our limits here. We know that y is going to go from 1 to 4. That was our first limits there. Z is going to go from y to 4. X is going to go from 0 to z. So we get a lot of stuff in here. It's a little hard to tell exactly what's happening here. So I'm going to kind of put in... I've gone ahead and outlined the part that's actually inside of all of these boundary planes. We'll go ahead and even take out these planes so we can see it a little bit clearer. So what we can see here is that our y values are definitely going from 1 to 4. That's what we're allowed to do there. We have this region D that's in the YZ plane that is bounded by from y going from 1 to 4, and then z going from y. So that I don't want to move that point. There we go. So we look at it straight on. You can kind of tell that this line here is just the line y equals z, or you can say z equals y. So we're going from z equals y to z equals 4. But then the x values are going from x equals 0 out to x equals z. That forms our solid here that we want to integrate over. Now, we didn't really have to look at the picture, though it is nice to actually see that, because what they've already done for us is they've written E as a type 3 region. In fact, they've written, you can say here, E is already a type 3. Wait. Sorry, I mean type 2. I guess type 2 was the one where x was a function of y and z. So this is type 2. And then here, whether or not you can say this is type 1 or type 2 region for D, it is up in the air because we're not really going over x and y. But since you could say y is first and then z, maybe you could say that our D in this case is type 1. You can say here D is the region in the YZ plane where y is between 1 and 4, and z is between y and 4. They've already kind of done that breakdown for us, so we don't really have to set it up ourselves. We're going to have to do that in some of the other examples. But the point here is our triple integral we can write down as an iterated integral using these limits. So y is going to go from 1 to 4, z is going to go from y to 4, x is going to go from 0 to z. We still have our function. That's actually not affected by our breakdown of e. And then we have to remember our order here. So this one here, the innermost integral sign corresponds to x, so that's going to be the innermost variable. Our second one corresponds to z, so we put dz next. And then finally our outermost one corresponds to y, so we put dy as our last variable. And now we just need to do these integrals. So for our first integral, for this innermost one, we are integrating with respect to x. We need to integrate this function with respect to x, and then plug these limits into that integral. Now, how do we actually integrate this one? This is actually maybe not the most straightforward integral to do. And one thing you might even stop and ask yourself at this point is, if I don't know how to do this one immediately, maybe a different order could have worked. And in some cases, that might actually be the case. We could possibly set this up differently, set up E as not a type 2 region, or maybe D as not a type 1. I guess this innermost integral only really depends on what type E is. So we'd have to set up E as maybe a type 1 or type 3 if we wanted to actually simplify this one. But I've actually already tried that, and it doesn't really avoid this issue. We still need to be able to integrate something where we have something on top and then x squared plus something. We need to know how to do that integral. And just kind of a reminder to you, so recall that we do know how to integrate 1 over u squared plus a squared du. This is actually a standard integral that we know how to do. And if you don't recall what this is immediately, there is a table of integrals in the back of the book, in the reference pages, so that if you have a physical copy of the book, they're the stiffer pages at the back. And if you look on, what is it, reference page 6, integral number 17, that's this particular integral, and it tells us that this integral is 1 over a times the inverse tangent of u over a, then with a constant. Obviously, when we're doing a definite integral, that constant's doesn't matter too much. But the point is that this integral turns into an inverse tangent. And that's what we have here, where x is our u and z is our a. So we can go ahead and do that. So this thing becomes, well, we saw the z there. Remember, we had to multiply by z, multiply whatever the result is by z. But because our a is equal to z, we end up with the 1 over z times the inverse tangent of x over z. That's going to go from 0 to z. Then we saw the dz dy on the outside. Obviously, the z and the 1 over z actually cancel each other out. We just get a 1 there. Now we need to plug in our limits. We still have all these integrals out here. Those won't change for now. When we plug in z, we have the inverse tangent of z over z, or really just the inverse tangent of 1. That's kind of nice. Then we have the minus the inverse tangent of 0 over z, or just 0. So actually, this turns out really nice. Everything kind of all the variables actually cancel out. The inverse tangent of 1 is pi over 4. Inverse tangent of 0 is 0. So we're really just looking at pi over 4 as our integrand. And since that's a constant, I'm going to even pull that out. We're going to say this is pi over 4 times the double integral of 1 over this region, over d actually. You can even rewrite this as pi over 4 times double integral over d of 1. And here we can actually even kind of cheat a little bit. Since we know that the double integral over 1 on a region D is just going to be the area of that region D, and we know what the region D is. Remember, it's just this triangle here. We can just evaluate this double integral by looking at the area. What is the area of this triangle? Well, this is a right triangle, so that's pretty easy. We know it has a length over here of 3, so 4 minus 1 is 3. Over here we also have a length of 3, again 4 minus 1. So the area of that triangle is just half of 3 times 3, or 9/2. So actually, this is pi over 4 times that 9/2 area of that triangle. Or in other words, we have 9 pi over 8. And if you don't want to do it that way, if you don't want to use the geometry of the situation, you could always do this double integral by hand. I mean, at this point, you're just integrating one anyways, so it's actually a pretty easy one to actually do the integral of. But if we can see a way to kind of cheat the system, why not take advantage of it? So it started out something that looked really complicated, turns out really easy at the very end of it. But the point here is how we actually are able to set this up. That's the thing that we really want to take away from this example. For our next example, our integrand is not too bad here. We're taking the triple integral of y squared, but now they haven't really given us what our region in three-dimensional space looks like yet. I mean, they tell us it is a tetrahedron and it gives us vertices, but they haven't listed out exactly how that's set up. So we're going to have to figure that out for ourselves this time. So I'm going to go ahead and plot these vertices so we can actually get an idea of what this looks like. So we have the origin, we have one where the first coordinate is changed to 2, same with the second coordinate and third coordinate for other points. Go ahead and plot those points. So we have 4 different points. I'm actually going to make these I don't know why it always tries to make them really big and label them all that. I'm going to go ahead and make segments connecting those points. So we have this tetrahedron in basically the corner here at the origin. And we want to be able to integrate over this tetrahedron. Now, we could actually set this up in any of our ways. You can view this as a type 1, 2, or 3 region. If we view this as a type 1 region, if we default to that, then what we can say is what is our top surface, what is our bottom surface? Our top surface would be this plane. This plane that actually is kind of cutting off this corner. And then the bottom surface would be the triangle down here in the xy plane. So you could say the upper surface is z equals, in this particular case, it would be 2 minus x minus y. That's the plane that we actually have here. Our lower surface is just z equals 0. If we look at our region in the plane, kind of just looking downward at it, this is now either a type 1 or type 2 region of the plane. And we can actually figure out what that is by looking at what is the top function, what is the bottom function. Our top function here would be the line y equals 2 minus x. Our bottom function would be y equals 0. And then our x values end up going from 0 to 2. So you can say y goes from 0, 2 minus x, and then x is going from 0 to 2. Now that's just one way of setting this up. We could actually go ahead and instead look at this as a type 2, in which case we'd say, in this particular case, you could say our upper surface what is the furthest away from the x-axis, or shouldn't say that. What is the furthest one away from the YZ plane? So if we're viewing this as a type 2, we going from x equals 0 for this one in the back over to the x plus y plus z equals 2 plane that's cutting this off. That is our furthest one out. And then you'd have to look at the triangle in the YZ plane, figure out what that is, do similar things. It's just in this particular case we have a lot of symmetry, so we actually can set this up in a lot of different ways. But obviously type 1 regions are kind of our default. Sort of like how type 1 was our default back with double integrals. So that means our triple integral, the integral over t, y squared dv, is going to be the integral. So our x's are the simplest one. Those are the ones with the numbers, so we put those first. Then y only depends on x, so we put that next. And then finally our z is going from 0 to 2 minus x minus y. We have y squared. And we have to remember what order we're doing these in. So this was z, y, and x. And at this point, the setup is already done. So the setup is usually the trickiest part of this. Now it's just a matter of doing the integration. As long as you don't end up with an integral that's really tricky to do. And this one we're not really going to, we're only dealing with polynomials here. Alright, so we integrate. What is the integral of y squared with respect to z? Well, y squared is a constant in this case, so we just have y squared z. Going from 0 to 2 minus x minus y. We get to plug that in. So really we're just replacing z here with 2 minus x minus y. I'm going to distribute the y squared. So we have a 2y squared minus xy squared minus y cubed. I think I'm going to run out of space here. Let me move stuff around a little bit. There we go. Everything's still there. I just move stuff up a little bit so I have more room at the bottom. We're going to integrate this polynomial. Hopefully you know how to do that by this point. If not, yeah. So the integral of y squared is 1/3 y cubed. So we have a 2/3 y cubed. We end up with a 1/3 xy cubed. And then over here we have a minus 1/4 y to the 4th. It's going to go from 0 to 2 minus x. Essentially, because when we plug in 0, we get 0, we're going to be replacing all these y's with 2 minus x's. And honestly, most of this wouldn't be too bad. It's really the middle term that's the trickiest part. With these, you could make with the first and third terms, you could make the substitution of u equals 2 minus x, and just treat this as a power, a third power and a fourth power, and do the integration that way. Unfortunately, for the middle one, that's going to be a little trickier. Though actually, that substitution would help quite a bit if you were to do it that way. What I actually did is I used some algebra to simplify what we have inside here. And I'll leave it to you to either verify what I've done here or work this out another way. There's a number of ways you could approach this particular one, but it turns out all this actually simplifies, all this stuff that's in here simplifies to 1/12 of 2 minus x to the 4th power. When we integrate that, like I said, here you can make a substitution of u equals 2 minus x. That means that du is negative dx. That means we end up with an extra minus sign here. Yeah, I'll just leave the 1/12 in there. But here we're basically integrating u to the fourth power, so we get a 1/5 u to the fifth power. But our u is just 2 minus x, going from 0 to 2. When we plug in 2, we actually get 0 because 2 minus 2 gives 0. It's when we plug in 0 that we actually get something. And the fact that we do get something for 0 is why we have the negative there. It actually cancels out when we subtract what we get when we plug in 0. So we end up with 1/12, 1/5, and then 2 to the fifth power. Well, 2 to the fifth power is 32. 12 times 5 is 60. Or we can even simplify this down by dividing the top and bottom by 4 to get an answer of 8/15. So that is the integral of y squared over this tetrahedron. For our last problem of this examples video, we're going to look at the triple integral of just z, where e is actually going to be a little bit more complicated than the previous ones. It's not going to be a polyhedron like we had for the other ones. E here is actually bounded by a cylinder and 3 different planes. So let's actually go ahead and plot this one too. I mean, that's really what you want to do for any of these problems, is plot what we're actually dealing with. What is the solid region that we're actually dealing with? So our cylinder here is y squared plus z squared equals 9. So you have this region here. We have our planes. We have x equals 0, y equals 3x, and z equals 0. So it might be a little bit complicated to see exactly what's going on here, but we are specifically looking at the part that's in the first quadrant. So first quadrant, you have to notice where the arrows are. So this is positive z, positive y, positive x. We're over in this near part. Let me stop that flashing. If we zoom in a little bit here, we're essentially saying that we're looking at this wedge here. We're looking at this wedge that's inside the cylinder between all these planes. And we want to know what is the integral of z over that wedge. And this is actually one where we could view it in multiple ways. We can actually view this either, you can say it as a type 1 region, where our upper surface is bounded by the cylinder. So we take the y squared plus z squared equals 9. We'd solve that for z. So z would be square root of 9 minus y squared. That would be our upper function. Our lower function there would be z equals 0, because we're only looking down to z equals 0. Then in that particular case, d is going to be this triangle down here in the xz plane. If you want to view this as a type 2 region, so in that case we're looking at what are our bounds as x equals a function and well, x equals a function of x and y to another function x and y. In that particular case, our x-axis here is what we want to think of as kind of our up and down kind of, even though that's not how we put it here. And GeoGebra doesn't really like me trying to put z as anywhere other than what we might consider up. But there, our top function would actually be the plane that we have here. We'd be basically going from this plane down to just the YZ plane. So we be going from x equals y over 3 down to x equals 0. In that particular case, our D, our region in the YZ plane, is actually this quarter circle. Finally, you can actually view this as a type 3 region. In that case, we want to think about y as a function of x and z. So here our up would be along the y-axis. What is our furthest out that we can go that way? What is our upper function? That's actually going to be the cylinder again. That's the furthest along we can go. And then we go down to y equals 0. Or, well, actually, no, not even y equals 0. We'd be going down to this plane again. So actually, we'd be going from y equals 3x up to y equals square root of 9 minus z squared. And in that particular case, we're looking at a region in the xz plane that we're actually trying to integrate over. So in that particular case, if we want to make y come out of the screen so we can see what's actually in the xz plane, it's going to be this section here, which is actually a quarter of an ellipse. It's specifically the ellipse x squared plus z squared over 9 equals 1. Now, I'm not saying that that's the way you want to do it. That one actually is a little bit complicated to even picture, let alone set up. Actually, I think the best idea here is to treat this as a type 2 region, because then, remember what I said, the x was going to go from, our x is going from 0 to y over 3, and d is a quarter circle. Specifically, the quarter circle given by our cylinder. And remember, the cylinder has a radius of 3 because we have a 9 here. I think that's the easiest way to do this one. You can try it yourself in the other directions if you prefer. All right. So first of all, I'm going to go ahead and leave it as a double integral on the outside. We'll come back to that double integral in a moment. I'm not going to try to set this all up all at once. You don't have to. You can do this in stages if you want to. So we're going to be doing a double integral over this quarter circle of the integral from x equals 0 to x equals y over 3 of z dx, and then dA to correspond to the double integral. Well, the integral of z with respect to x is actually pretty simple. It's just going to be z times x from 0 to y over 3. So we just get to plug in y over 3, so we get a 1/3 yz dA. At this point, it's just a double integral. We don't even have to think about it as a triple integral anymore. The only thing here is that we're not in x and y coordinates, we're in y and z coordinates. But now we can actually use any of the techniques that we already know how to use from earlier in the chapter. Specifically, since we're dealing with a quarter circle, it might make sense to use polar coordinates. Though we do have to keep in mind there, since we're not in x and y coordinates, if we're going from x and y and change into y and z, we might have to figure out what would actually correspond to r, what would correspond to theta, and all that kind of stuff. Essentially, I'm going to let this y still play the same role as y did over here, but z is going to play the role of x. That's going to mean that y is going to be r sine, like it was before, but then z, because it's going to play the role of x, is going to be r cosine. We're going to need that for when we plug in x and y, y and z into our integrand. So if we set this up, well, we're going around a quarter circle. The quarter circle means that theta is going to go from 0 to pi over 2. The radius of 3 means that r is going to go from 0 to 3. I'm actually going to take this 1/3 and place it outside. The y is going to be our sine. Z is going to be our cosine. Remember, when we use polar coordinates, we do need to put an extra r. Then we have dr d theta. Since everything in here is actually a product of something with r times something with theta, I can actually split up my integral, so I don't have to deal with everything all at once. The stuff that deals with theta is the sine and the cosine. The stuff that deals with r is, well, we have an r here, an r here, and an r here, so we have an r cubed. This first integral, I would evaluate this by making a substitution. I would set u equal to sine. That means that du equals cosine d theta. And so essentially this integral just becomes the integral of u. The integral of u is 1/2 u squared, but our u is sine, so we have a 1/2 sine squared from 0 to pi over 2. Integral of r cubed is just going to be a 1/4 r to the 4th, still from 0 to 3. When we plug in pi over 2, sine of pi over 2 is 1, so we get a 1/2. Minus sine of 0 is 0, so that's just going to be 1/2. Here we get to plug in a 3, so 3 to the 4th power is actually 81. But then putting in 0 gives us 0. So we have 81 divided by 3, 2, and 4. Well, 81 divided by 3 is actually 27. And then the 2 and the 4 becomes an 8. So our answer here, or the full result of this thing, is 27 over 8. That's the integral of z over this wedge. I don't know a better term for it. I'm just going to call it a wedge. But again, there are other ways of doing this. I basically just took advantage of the fact that we could even view this using polar coordinates in order to avoid having to do anything like z equals square root of 9 minus y squared. Because I'd like to avoid using the square roots if I can possibly do that. Nothing here ever did anything other than, well, I guess the most complicated thing would be dealing with the trig functions. But ultimately that just came down to a fairly simple substitution. So, again, multiple ways of going about this. Try things out. If something doesn't work very nicely, try something different. Then a lot of this comes down to practice. I mean, that actually turns out to be the case a lot of the times in mathematics. You have to practice a lot of problems in order to get a good feel of what would be the best way to tackle a problem. Because there's frequently multiple ways of doing them. But I'm going to go ahead and leave this example video right here, and we'll get into some applications of triple integrals. So similar to some of the stuff that we did with double integrals. So I'll see you in that video.